don't know how many of you are coming here for the first time. In case you are very good. Just to tell you, Chai and Why is a outreach activity of TIFR where we try and bring you something from the world of science every 2 weeks. The first Sunday of the month, we are always here at Prithvi Theatre in Juhu. On the third Sunday, we are always at Ruparel College in Matunga. And if a month has a fifth Sunday, like September will have a fifth Sunday, then we are in South Mumbai at Alexandra School in Fort. And just to tell you about the next few sessions coming up, please keep your phones on silent, simply because I plan to start another program called Vada Pav and How, which looks at how things work, and I think we should start with cell phones. We can open them up, and I always need samples to try, so if your phone rings, I'll use it. Okay, so the next one, August 18th, 2 weeks from now, is in celebration of National Scientific Temper Day, which happens on August 20th. And this is going to be by Aniket Sure from HBCSE, who is going to look at, is it scientific? He's going to explore the world of all the random forwards you get on WhatsApp and Twitter and everything else, where there are all very scientific sounding things which are really difficult to figure out. So we're going to look at many of these and see how do you figure out if something is scientific or not. So that is on the National Scientific Day Temper Special happening on August 18th. Remember, National Scientific Temper Day is August 20th. Okay. September 1, a month from now over here, we are essentially celebrating Chandrayaan 2. Okay. We are going to have Professor Mayank Vahia, who just retired from TIFR and is right here at NMIMS. He is going to be talking about various moon missions. And remember, Chandrayaan 2 should reach the moon on September 7th. So this will prepare you for it. Mainly looking at how do we use Earth's gravity to send something to the moon. So that's how ISRO managed to do it with very little budget compared to other missions. And we look at all the science that you can do, which has happened all from Apollo 11 to Chandrayaan 2. So that's over the moon, a month from now over here. And the best way to find out about us is on Facebook or Twitter. So please follow at @JaiandY. And you can send us feedback, you can ask questions, and let us know how you would like it. And I should also announce that August 9th, coming up very soon, is going to be the March for Science India. This is from Ruparel College, one of our venues, to Shivaji Park. It's a march for science, it's not a march against anything. We are supporting the cause of science, so don't have to worry about it. It's not a protest march, it's a march celebrating science. So please do spread the word, join us, help us, whatever you can. Okay, so with that, it's time to get to today's session, which is a very exciting topic, which certainly should interest all of you from Mumbai. It's called Physics and the City of Mumbai, and it's a pleasure to welcome Professor Vijay Singh, who is a colleague for the last several years at the Homi Bhabha Center for Science Education. He just retired from there and now is at the University of Mumbai DAE Center for Basic Sciences in Kalina. But he is trained as a physicist from SUNY Albany, worked in solar energy, came back, was at IIT Kanpur for 20 years teaching physics, then moved to the Homi Bhabha Center for Science Education and has been one of the leaders of physics education in India. Very strong links with the Physics Olympiad and all the Olympiad programs in general. And of course, most interesting, he can compose poetry, it's always nice to have a chat with him. And he's one of these armchair dreamers who, with a pen and paper and a little bit of science, can analyze things that you would have otherwise taken for granted and tell you some wonderful stories. And I'm sure he's going to do that about the city of Mumbai. Okay? So, over to you, Vijay. So, just remember, this is only for the camera. So, there is no mic for the room.
Okay. Oh, so I have to yell?
You have to yell.
Okay.
This is only for the live webcast.
Oh, that's for the live broadcast.
Yeah.
Okay. Okay. Thank you.
Sit back and enjoy.
Thank you, Arnab, for a very effusive introduction. Before I begin, may I ask, am I clearly audible in the back? Okay.
Otherwise, why didn't people come in front? Yeah, today
okay.
We don't have 200 people here. Come on.
Yes.
So, prevent them from
may I begin by thanking the Chai and Why Committee and Prithvi Theatres for having me over today. As someone who grew up in what was once Bombay and what is now Mumbai, and so have many of you, okay, we have grown to develop an attachment to the city, and we tend to put our stamp and our own perspective on the city, and in my case, it happens to be physics. Okay. So several years ago, I think it's about 100 or more years ago, there was a poet from Lucknow who came here. He saw the sights of Mumbai. He went around, he went atop Malabar Hill, and he saw the what is known as the crescent, the Queen's necklace, which is Chowpatty. And then he went to Haji Ali, and he saw the crimson sunset, and he exclaimed, "Khushnuma Bombay, tujh pe piro ka saya, Khushnuma Bombay, tujh pe piro ka saya, jaise suna tha, tujhe waisa hi paya." This is Nazir Ahmad in 1903, more than 100 years ago. Okay. So let us focus on this minaret and indulge me while I do a small calculation regarding the minaret. Why a minar? Okay. In Arabic, a manara means a lighthouse or a signaling tower. Okay. And that is because if you go atop a minaret or a manara, okay, you can actually see further. And why is that? That is because the horizon is limited in sight, and that is because the earth is round. Okay. And that's why you need a taller structure to see farther away. Okay. Right. So as I said, kindly indulge me as I run you through a small calculation. This is the so-called Pythagoras theorem that I'm applying to the earth. Okay. And let me show you this figure over here. This is the height of the Haji Ali Tower, which is about 25 meters. Okay. And this is the radius of the earth. They are different scales. The height is 25 meters. The radius is 6,400 kilometers. Okay. So that's the difference in scale. What you can do is you can see up to the line of sight is up to the tangent to the circle, which is this cross section of the Earth's sphere. You apply the Pythagoras theorem. This is d. You have r plus h to the whole square minus r square is d square. Unfortunately, I've got an x over here. It should be a d. Okay. And then you do something which is very interesting. You do a small approximation. You ignore the h square in that term, okay, to get a very simple expression for the distance that you can see. Okay. And if you do this calculation, the Haji Ali Tower is 25 meters, I remind you. Okay. And you have to deal with mixed units, 6,400 kilometers versus 85 meters. Okay. You get about 18 kilometers. That is how far you can see. If you are a human being, you are about 1.8 meters tall, say. Okay. You can see about 5 kilometers. Now, this is a simple enough calculation, but it has several lessons for us as a kid, okay, which we tend to perhaps overlook. Okay. The first is how to make an approximation. How do you ignore a small quantity with respect to a large one? The second is, how should I put it? You should basically how to deal with mixed units. It happens all the time. Okay. 6,400 kilometers versus 25 meters. The third and the most important is what I call scaling laws. The distance that you see scales with the square root of the height. Okay. This quantity 2 into r is a fixed number. It's the radius of the earth times twice, or the diameter of the earth. That does not change. What changes is only the height. So if you do one calculation, you can do the other one very quickly, because you know it is square root of h. If you are four times taller, you can see twice as far and not 4 times as far. Okay. And the fourth one is the most important. Is this true? Can I see? The answer is no. Finally, the test is with the observation. I cannot see that far because light attenuates as it travels. And given the pollution and the haze in Mumbai, you will never be able to see 18 kilometers. or even 5 kilometers. Okay. So the final test is in the experiment or the observation. So do this simple calculation. You learn 4 things if you are attentive to the calculation. Okay. So I'm continuing with the introduction. Here is a scientific comparison between Mumbai. Yes, sir. William.
Can I ask you a question?
Yes, yes.
This x
Hmm.
is the direct distance,
Ah.
but along the surface,
Yes, yes.
that's the distance which,
Well, you're saying that this is this distance, and you're talking about this distance. That is not very different. That's another approximation, of course. Yeah. The two are very close to each other. Okay? Because this height is, after all, minuscule compared to the radius of the Earth. So the Earth is flat. In a certain sense, you make a flat Earth approximation right here. Thank you very much. That's a good point. Okay, here's a comparison between Mumbai and the world scientific history, maybe British scientific history. 1661, Mumbai or Bombay at that time, also called Bombay, was given to King Charles II by the Portuguese as a dowry. So the system is not unique to India. The dowry system was there all over. Okay. Around the same time, Robert Boyle in England proved Boyle's law for ideal gases, that if you have a container, okay, if the temperature is fixed, the pressure is inversely proportional to the volume. About a few years later, the British East India Company, the biggest multinational corporation, or the largest one and the longest one in history, leased the 7 islands of Mumbai from King Charles II. Around the same time, the Philosophical Transactions of the Royal Society published the first peer-reviewed journal. Okay. 1687, a very landmark year for physics, Newton published the Principia. The same year, the British East India Company changed their headquarters from Surat, which is just north of Mumbai, to Bombay. Okay. 1802, another landmark year. Okay. Thomas Young proved that light is a wave. It doesn't have a straight line propagation. It has a wave character. Okay. Given his famous Young's double slit experiment, the Treaty of Bassein, in which Bajirao II, I think it was Bajirao II, the Peshwa, handed over sovereignty to the British. Okay. So you can see, while the British were making great strides in science, we were slowly and surely sinking under the heels of colonialism. So now, what are these 7 islands? It's right here. These 7 islands were 7 separate, or 9 in fact, and then they were amalgamated into one in the 19th century. Okay. And that's about 70 kilometers square. The rest of Mumbai is another 370. So overall, it makes about 450 square kilometers of land. The population is actually it's 20 million now. It's 20 million and growing, which makes for a population density which is exceptionally high in the world, 40,000 or more, 45,000 per square kilometer. In case you want to have an idea of what that means, each one of us has 25 meters square of space in Bombay. That is to say, it's 5 meters by 5 meters. Okay, and that's it. That's the real estate problem of Bombay. Right? You know, if you are a physicist, you will think of charge density. So charge density is something on a metal surface. You know, that is what gives. If it's a spiked surface, you get this lightning discharge or sparking. We are so high that sparking is quite possible, but it rarely happens. In Bombay, as they say, the Mumbaikars have a large tolerance limit. Okay, the tolerance is very high. I personally grew up in this place called Mahim. Okay, and it was a wonderful place to grow up in. When you were there, when you were small, you thought it was a lousy place. Okay, why were you not in Pedder Road or something like that, or Warden Road? Okay. But it was a great place because it had a mixed population of all types, 1/3 Hindu, 1/3 Christians, and 1/3 Muslims. And they came in all hues and colors, a very differentiated lot. Okay, and depending on whom you spoke to, the other guys were all inferior to them. Okay. So not a very politically correct place in those days, but a very wonderful place. Okay, by the way, for example, if you looked at the Muslims, they are not an undifferentiated lot. There were Shias, there were Sunnis, there were Memons, there were Bohras, there were Ismailis, and a few Ahmadiyyas. And you got to learn about all of that by osmosis, not that you went and read about it in Wikipedia, okay, by just being there. Okay, so the way to understand the streets of Mumbai is to look at a metric called the Manhattan metric. Okay, the Manhattan metric is basically perpendicular roads. There is a straight road. This is Manhattan, by the way. Here it is. This is a Manhattan. Okay, it is almost like like the island city of Mumbai. You have straight roads and you have perpendicular roads. The straight roads are called avenues. There are 8 or 10 of them, and the perpendicular ones are called streets. They are closely spaced, okay, and they are basically east-west, and there are about 100 of these. So if you walk 40 blocks, it's like 1 mile. As opposed to that, there is something called the Moscow metric. Okay, it fans out from the Kremlin, and it goes out in a radial direction. Mumbai is right here. It has got more or less approximately a Manhattan metric. Okay, the roads run, these big roads which run, there used to be the Lady Jamshedji Road, okay, which went on and became some other road right here, the SV Road or whatever you'd like to call it, the Ghodbandar Road, which became Tulsi Pipe Road. So these are on the west side. On the east side, you had the Muhammad Ali Road, which now becomes the Ambedkar Road, and then the VN Purao Marg, which goes into BRC. Okay, so these are the perpendicular roads. Okay, these longitudinal roads, north-south, and then there are these perpendicular roads, which are not too many because you have to cross many tracks, railway tracks. Okay, so there used to be the Tilak Bridge or the Kennedy Bridge. Okay, so there are few of them, and they're not, they are not very well connected from east to west. Okay, but that's the way to understand it. Delhi, on the other hand, fans out from Connaught Place. It has the Moscow metric. Okay, so that's the introduction. Let's come to the main body of the talk. And I can only present you a few snippets. I won't be telling you all the stories that I have or presenting you with all the slides that I have. If you are in Mumbai, there are some pivotal experiences. There are certain experiences which have touched you at multiple levels and at multiple times. Okay. The local train, the local rain, the Bombay rain, okay. The real estate problem, okay. The beaches of Bombay, okay. And finally Bollywood. Okay. And there are many more, but these are some pivotal experiences. Here is the Mumbai trains. Oh, here it is. Okay. The first train, of course, and there was a wonderful talk by Arnab, and what was his name? I forget. Mahesh. And is he there in the audience today? No. Okay. So last week, about 2 weeks ago, on the Bombay trains. Okay. So I will talk orthogonal to that. Okay. But this was common to both of us. The first train started 160 or 70 years ago, and it went 34 kilometers from Boribandar all the way to Thane, making a few stops on the way. It was a steam engine train. It took exactly 1 hour and 15 minutes, as it stopped at 4 places. Now, that is 2014 data, the fast train takes 45 minutes with 4 halts. The slow train takes 1 hour, and this is about 1 hour and 15 minutes. So it's like 1 minute of progress per decade, every 10 years. So one experience is that people, and this is, I guess you all know about it, at least 10 or more people are killed on the tracks every day. Okay, right? So sometimes it's as large as 18 or 20, sometimes as few as 5, but every death diminishes us in some way. And here's a small calculation which probably illustrates why you should not cross a track. Okay. Supposing you are crossing a track and you are stuck for some reason. You fall down, you can't get up, and a fast train is approaching you. Remember, the fast train is about 25 meters per second, 90 kilometers per hour, pretty fast. Okay. If you are 200 meters away, can the motorman or the motor person nowadays, can she stop the train? Yes or no? I want you to respond. Very good. What about, who said no? 300 meters? 300 meters? I think you have to be louder. How many people say no? You say loud, you can yell. Okay. 400? Right. 500? Right? Definitely yes. Definitely no. Okay. Because the maximum deceleration of a fast train is half a meter square, half a meter per second square. Okay. That is because if you try to do it faster or harder, the whole train will overturn. So instead of saving one person, you'd be killing about 1,000. Okay. And if you do a small calculation, which every kid, there are some kids I can see, v square is equal to u square plus 2as. Okay. V is 0 because the final velocity is 0. The initial velocity is 25. I remind you, this is just half. This half cancels with the 2, and 2 and 2 put together gives you 625 meters. And then, even this is not correct because you have to consider the reaction time. The reaction time being, say, approximately 2 seconds for the motor person. Okay. That's another 50 meters. This is the minimum. Okay. So this is one way to convince somebody that they should not be crossing the tracks. However, I have to tell you that this is not the full story. People do not survive while crossing a track for reasons which are more important than this calculation. One is habit. If you have been doing it for 50 times, you think you can do it for the 51st time, and you are wrong. Okay. The second is, these trains usually have loud horns. Now they have toned it down. The loud horn actually frights you. You know, there is this thing called fright, flight, etc. So this is actually more like you get frightened rather than you run because of the loud horn. And the third is actually a very interesting reason, which is between psychology and physics, I say. It's a mix of psychology and physics. When you see a thing approaching, you judge its speed not as a physicist by taking meter sticks and clocks. The way you judge it is how much distance does it travel given its body length. Okay, here's the body length. For example, the fast train or a bogie of a fast train, a coach. This is a coach of the fast train. It's 25 meters, 20 meters, say. And the train is traveling, say, at 20 meters per second. So that's like one body length. Correct? One body length per second. Okay. Is this clear? This calculation? You actually calculate it not by meter sticks and clocks, you judge it by its body length. If you take a small gutter rat in Mumbai, and there are several of them all over Mumbai, thousands of them in fact, hundreds and thousands of them. Okay. Actually, you can do a very interesting talk on what is called the Bombay biome. You know, the Bombay biome has gutter rats, they have cockroaches, all these animals which live in semi-darkness, okay, and they actually, therefore they have antennas, you know, and you can do a very interesting study around that line. Anyway, the gutter rat is about 20 centimeters long, and it travels at 2 meters per second. So that is 20 body lengths per second. So it gives the impression that it is running very fast. A large body, even if it is moving fast, gives you the impression that it is moving slow. That is why you have this phrase that an elephant is lumbering towards you. The damn thing is running very fast, okay, and you better run, but you can't escape him. Okay. And the other thing is, you see an ant is scurrying. The word lumbering and scurrying are because of this psychology and physics mix. Body lengths per second is what you should do. Okay. That's why when you see a train approaching, you think it's very slow. You can do it, but you can't. Okay. Never ever cross the tracks. Okay. There's another thing. Okay. When I grew up in Mahim, there was a section of the tracks which was very prone to accidents. Okay. And there's an old lady who told me that you should not go near it because the spirits of those who passed away on the tracks, unfortunately, they congregate there and they tend to drag you in. Okay, so it was that kind of thing. So basically, it is actually half true. This thing happens because what happens is when the fast train is moving, the air beneath is getting dragged. And you're right next to the tracks. If you're standing next to the tracks, if you're right next to it, the air behind you is stationary, and you feel a small tug, a small push towards the tracks, a very small one, a perceptible one, not something that will push you, but you do feel this small thing, and that is attributed to something called Bernoulli's principle in physics. That is what keeps a plane afloat, or at least partly. It's not the whole reason. That is what makes a ball swing in air, a fast ball. Okay? And that is what pulls you in. In fact, if you are driving in a small car, if you are the driver, not if you are one of the passengers, if you are driving in a small car on the Pune highway and a monster truck passes you by, okay, you will feel a slight sideways lateral pressure or a lateral tug towards it. Okay. Don't do this. Okay. Whether you believe in Bernoulli or in that Booth or Bernoulli, you are not supposed to do this. Okay. There is another thing, if there's another, all these phenomena are actually something worth observation, and you have all observed it. You get off at Andheri station. How many of you are from Andheri? Yeah, a lot of us. Or if you're getting off at VT station. Before you get off, at least in one bogie, the one coach as it is called, technically, at least 100 people have descended before the train comes to a halt. So the train comes to the station, and before it comes to a halt, every compartment, about 100 people are off the train. They are in such a hurry to run somewhere that they do this, and every once in a while, somebody makes a mistake, a very dramatic mistake. He or she jumps off in the opposite direction to the motion of the train. Jumping straight is bad enough. Jumping in the opposite direction, or just alighting, if you're not even jumping, just alighting in the opposite direction is fatal. Here is the example. August 18th, 2018, about 7:15 in the evening at Thane station, a person called Hamid Jawal tried to deboard the train. He fell, his head was fractured, and he died. This came out in the newspaper the next day, and they all asked, who is this person? Nobody knew who he was. Okay. And they all, after a few days, you found out that Hamid Jawal was from Bangladesh, far, far away from home. Here is how you can understand this. The train is moving in this direction, and you alight in the reverse direction. This is the reverse direction. So this is the face. The face is in this direction. I'm drawing the face. It's actually a caricature, okay? And this is the train, okay? The momentum is still of the train because you're alighting. You still have the velocity of the train. That is the first law, the inertia law of Newton. Okay. So the v is in this direction. The momentum is m into v, okay? And then there is a term, which I will come to again, called the moment of the momentum, called the angular momentum. Okay, the angular momentum is mass into velocity, the momentum into L by 2, half the height. Okay, this is a rough calculation. Before you alight. Once you come down, you are grounded. Okay. The expression for the angular momentum changes. Okay, if you are in 11th standard, you would understand this expression. The expression becomes m L square omega, which is the angular velocity, the angle changed per second, divided by 3. Okay. It doesn't matter how heavy you are, whether you're a fat guy or a thin person, the m cancels out from both sides because angular momentum is conserved. There's a very important theorem here in physics called the angular momentum does not change. The expression has changed. The term does not change. You equate the two. The mass cancels out. You get omega. That omega turns out to be 90 degrees per second. Now 90 degrees per second means if you have gone down like this, you have fallen within 1 second. Nobody can help you. You can't help yourself. Nobody else can interject and help you out. Okay. So this is a fatal deboarding, And you can never do that. You would have experienced it once in a while. You have probably been lucky. You have probably deboarded a bus or a train in the opposite direction, and you must have felt this very scary feeling that you're going to fall. Okay. The back of the head comes crashing down in 1 second. If you alight in the forward direction, what you normally do is you just keep stepping forward. Okay. So you sort of take care of that angular momentum conservation, but it is not recommended either. It happens all the time. Okay. I should show you the video where people are alighting, and usually from the ladies' compartment. I mean, all of them, alighting at the same time, jostling and alighting. Ladies, gents, everybody. I mean, we go to Churchgate Station, it's quite a sight. It's a riot. You should just give yourself some time to observe all this. Okay. Okay. Boliye, please.
Does that, if you are sort of going in the opposite direction on an escalator, does it apply at all, or that's a completely different?
What do you mean, opposite direction?
I mean, if the escalator is going up and somebody is trying to climb down, or vice versa?
In an escalator? Yes, it would. It would. Yeah. The audience, the question is, in a mall or something normally, or even at the railway station now they have escalators, we should be thankful for such small mercies which the railway provides, once in the other station, Andheri station. So when an escalator is going up and you try to climb down, would you feel such an effect? To a certain extent, yes. Okay. The law of inertia works. When you jump, as you're stepping off, because you have one step already in, it helps, but as you're stepping off, you'll feel tucked in the opposite direction, right? So, okay, now this is why, I must once again congratulate all of you for braving it out and coming here on this rainy day, but getting monsoon is a experience that we are all familiar with. Okay, the monsoon is such that you always get wet, not just wet, even drenched once or twice every monsoon, with all the precautions that you take. Okay, you always lose an umbrella or two. I've already lost mine about 15 days ago. This is my second right now. Okay, so, so, and also the other thing is that if you put an umbrella somewhere, somebody walks away with it. So that's a very interesting thing. These are some sites from July 5th, 2005. July 26th, 2005. Okay, right. They're all drowned. There were some reports then. Okay, there were certain reports that perhaps certain people were trapped in their cars. They couldn't open the window. The window was not, because it's an electronic system, and they were trapped and they could not open the door. Their car door could not be opened. Okay. Am I clearly audible in the back? Okay, thank you. Okay. Please warn me if my voice drops. Okay. So you can do a small calculation to just verify if this is true. Okay. Here is the calculation. The calculation begins with a quantity called calculating the pressure. The pressure exerted by the water on the car door. Okay. The pressure is given by an expression which is rho into G into H. It's a very difficult term for some of us who are not in science, but G is the acceleration due to gravity. Assume it to be a number like 10. Okay. Rho is the density of water. Take it to be 1,000 kilograms per meter cube. Okay. 1,000 into 10 is 10,000. H is the height of the water column. Okay. So if the height of the water column is even like 2 meters, it's even like 2 meters, H by 2 is 1 meter. Or even if it's 1 meter, this becomes 5,000 in some unit called a Pascal. It's named after Pascal because it's Pascal who proposed this law. Okay. This is the same law which explains many things to you. If you know this law, you will probably understand blood pressure. The blood pressure is 120 millimeters of mercury in the systolic phase and say 100 millimeters. The blood pressure in the leg at the leg point is at least twice that at the heart. That is because of this rho GH. The blood pressure in the head is a little bit less, at least 50% less than over here. Okay. That's why the giraffe needs to have a very hard and strong heart pump. Okay. It can kick the blood up to the brain of the giraffe. You want to kill a snake? You don't have to beat it to death. Just hold it upside down for a few minutes. It will die because the blood gets gorged into its brain and it passes away. Okay. So this is very important quantity called pressure given by this expression rho GH. Okay. Well, yes, to some extent. Yeah. If there are of course certain corrections to be made, biological corrections, but okay, yeah, yes. They'll need a stronger heart. Okay. So that's a nice observation. I should remember this. Yes.
Some snakes climb the trees.
Huh?
How does it happen? Snakes climb
Yeah, but I'm holding it upside down. So that the heart cannot pump the blood up then. I hold a snake upside down for a few minutes and it will pass away.
And that's why the natural tendency of the snake is to raise its head.
Yes, when you hold it, it will try to get up, Huh?
Always go up.
Yeah. And you think it's trying to bite you. No, it's just trying to survive. That's all that it wants. Okay.
So what happens when you do Shirshasana?
Or you're pumping blood into the brain, yes. Not recommended for people with hypertension like me. Yes. Good point. You have a good heart, so that will work out, So, basically, you need a mighty heart, so they say, As they say, there is a Spanish phrase, you ain't got corazon, you ain't got nada. That is, if you don't have a heart, you have nothing. And so anyway, just. Yes, ma'am.
Even when you're doing Shirshasana, you're not doing it for like 10 minutes or 15 minutes.
Right, yeah. Just a couple of minutes, yeah. Yes. Yes, yes.
BP and some eye-related disorders and all that. Retinal problems you have,
Yes, yes. I mean, it helps also. I'm not saying it doesn't.
That is for healthy people without any
Yes. So now we are getting into any doctors in this audience, so they can even contribute. It's not good because if you have hypertension, if you have cervical spondylitis or some neck problem, perhaps it is not good because you're putting a lot of load on it. Okay. So anyway, the force on the car door is just pressure into area. Okay. And that gives about 5,000 newtons. Okay. So this is the pressure from outside. You think its water is steady. The water is not coming towards you like high tide or something like that. It is just there, it is applying this pressure. Okay, the force is 5,000 newtons. A human being is about, say, at the most 100 kg or 80 kg. He can put a force of 10 times that. Mass into G, again the same quantity G, 10, so 1,000 newtons. So if the force from outside is 5,000 and from inside it is 1,000, even if there's two of you, you cannot open the door. Okay. So it's quite likely that some of these stories are true. You're trying to verify, after all, people say all these things. Okay, so you are trapped. Okay. Here's another one, the wall collapse, which happened in Malad. Okay. Here you don't talk about the force. Wait, this is the force. You talk about, remember what I said, the moment of the momentum. You talk about the moment of the force. And when you do that calculation, okay, the wall was a very long wall, I think. It was a very long wall. It collapsed in the middle somewhere. Okay. The moment of the force is proportional to the length of the wall and the cube of the water height, not just square. It's actually the cube of the water height. Okay. So if you have a very long wall, what happens is that the moment or the force applied at the bottom, if I can call it, of this wall is proportional to L into H cube. If you half the wall, okay, the length of the wall, you are half. If you half the height of the water, you are 1/8. So if you are making a large, for example, if you look at dams or something, people know this all along. If you look at dams, they have a large wall, a very large running wall, but at the bottom it is very, very thick. The dam walls are actually thicker at the bottom than at the top. So that is the calculation that one needs to do to figure out if this is possible and how it would help. Okay. Here is another small calculation. I don't want you to look at this. Okay, I can just do it. I figured out that there is a simple way to do it on water harvesting. We are having a lot of rain. So can you see this? Is this visible? See, the point is, if you look at today's newspaper, yesterday's newspaper, the water requirement of Mumbai is given to be 15 lakh million, whatever that means, liters. This is the water requirement for the whole year. Look at today's Times of India, page 2, it's there. It says 14.5. The area of Mumbai, if you can allow me to exaggerate just a little bit, is 600 square kilometers. The rainfall in Mumbai is 2.5 meters per year. Okay, 240 millimeters they say, 2.5 meters. Multiply these two. 6 into 2 is 12, 6 into 2.5 is 15. This also works out to be 15 lakh million liters. If you do water harvesting, okay, there is no need to have lakes. However, it's well known that you cannot harvest this entire water or something. So say if you harvest 10%, you get 10% of Mumbai's annual need. So I'm not saying you harvest all of it, but just 10%. Okay. So this is a very simple calculation. If you are not convinced, you go home and you can just carry this through. Okay. 15 lakh billion is 15 into 10 to the power 11, so to say. Okay. And there was a rather convoluted way in which I got all this, but that is the simplest one, the one that I've displayed on the whiteboard. Okay. So let me just change tracks. Is this a point to stop, or should I continue?
Good point to stop.
Good point. Okay, you can take a chai break, and I will continue with something which is. So I want to talk about Bollywood and some other things.
Okay, so we're going to talk on Bollywood and more exciting stuff when we are back. Online audience, give us 10 minutes. We're going to take a break for a quick chai. That's one of the reasons to come for the live one. Okay, so if you're watching online, hold on. We'll be back in 10 minutes with interesting things on Bollywood. Don't go away. And just grab a chai and come back. We'll also try and get some better light in the meanwhile. Okay, great. Thank you.
Thank you very much. Okay. So another pivotal experience in Mumbai is, of course, the housing problem. Okay. Real estate. Okay. That's basically, how should I put it? Everybody and his brother is an expert on Bombay housing problem. Okay. Right. Whether you're a peon, a panwala, or a professor, you just have to say that I want to sell my house, and I want to give it on rent or something, and you have 10 people following you. So, but not that I have a solution to this problem, but I'll tell you how to understand this problem. I have already told you one way, and that is each person has only 25 square meters, or 5 meters by 5 meters is all that you have. Okay. Okay. Here is what you see. These are slums. Oh, okay. So this is the Mahim Church. Okay, Mahim Church, St. Michael's Church it is called. Okay, and you see these large windows. Okay, these large windows are there because they play the role of nutrition as far as a building is concerned, a structure is concerned. They let light in. They would let you light in. Otherwise, you have to have a large number of lamps and bulbs and tube lights, etc. So basically, a large window is allowing you to get light in. Here's another example. This is a mall, one of the malls of Mumbai. You can see this. It allows light to come in. Cells divide. Okay. Why do they divide? Because if they didn't, they would become unviable. There's a cell. Okay. The nutrition comes from the surface, which is r square, 4 pi r square. It has to support the entire volume, which is 4 pi by 3 r cube. Okay. So to support that volume, the cell better divide, otherwise it becomes unviable. R cube, r square by r cube is 1 by r. The larger you are, 1 by r is smaller, so your survivability goes down. Okay. Here is another example. This is the small intestine. Okay. You might say, why? I'll connect it with the housing problem. Just give me a minute. Okay. Okay. Why am I showing you the small? It is, you can see it's a misnomer, of course. We all know it. It's 22 feet long. And if it was a cow, it would be 80 feet long. Okay. And it's convoluted like this. Okay. Moreover, if you look at the inside, it has these hair-like protrusions which are called villi. Okay. This is when you get nutrition in, okay, it has to be distributed in the body, and this is how you increase your surface area, okay, by convolution and by this villi. Okay. Same thing, you need nutrition in, you need air in, you need oxygen in, okay, and you need these alveoli. It's called alveoli because you need millions of small air pockets so it can absorb better. Okay. This is the modern bath towel. Okay. This is actually inspired by the villi. If you have a flat piece of cloth, like my handkerchief or something, it won't dry you. But if you have these small hair-like protrusions, no, it actually helps to dry better. It increases the surface area. Basically, the idea is somehow you have to increase the surface area. Okay. How do you do this? Okay. Here is the airport. This is how they do it. Okay. This is the modern airport, not the old ones. The modern airport has all these alveoli. They are called air jetties, of course, but the way you view it is these are the alveoli. All these cars, aeroplanes, the planes can just park here. You are increasing the surface area for parking by having these alveoli. I'm sorry, villi, not alveoli, but these are the villi. Okay. So these are the villi you have. Right. Here is Dharavi. I've taken it from the internet, this picture. Here is a woman in Dharavi trying to dry papad. If she spreads it out, she can have 6 papads in this space. But if she goes to the third dimension, okay, she can dry 12 papads. Okay. So the idea is you go to the third dimension. Okay. That's how it's happening. Here is Bombay. You have gone to the third dimension. You try to go up. The flat space is 2-dimensional, this is 3-dimensional, and this is between 2 and 3. Okay. So you have these high rises, these very long, ugly looking structures which rise on and so on. Okay. All the cities, all the coastal cities that you see will have this kind of structure. They are all similar, whether it is Shanghai, whether it is Kuala Lumpur, whether it is Seoul, or whether it is Singapore, they are all similar. In fact, you can do a calculation called the fractal dimension, which I can run a more advanced student through. You do a fractal dimension of the structure, it is between 2 and 3. So it's neither 2-dimensional nor is it 3-dimensional, it's in between. Okay. You go to the third dimension essentially. Here it is. You've gone to the second higher dimension to accommodate passengers. Trains, there are double-decker trains with 3 or 4 decks or something. Go to the third dimension. Not recommended. But you go to the third dimension. Okay. So that is the only idea you have. Given space, it is just 2 and 2. You can just arithmetic. You go to the third dimension. Okay. You pay a price for it. You get isolated. Now there are people who live in these tall structures who have absolutely no idea about the real world. Okay. But that's all that you can do. Okay. Okay. So I will go to switch topics. These were the 4 main topics, and of course, one was left out. But let me just go to the sea link, the pride of Mumbai. It's about 5.6 kilometers long, okay. And you should not, of course, won't do the kinematics for it, but there is an optical phenomena I want to draw your attention to. You come from the north side to the sea link, come from Bandra side, and you look up. It is a double-stranded cable which holds up the sea link. You can see these cables, these are double-stranded. You look up. What you will see is something amazing. You will see shifting patterns. Okay. This is how it looks. You see these patterns, these circles, they keep shifting as you are approaching the double-stranded cables. Okay. These are called Moire patterns. Okay. They are used to detect imperfections. Here it is. You take a piece of graph paper. You can go right now after this talk and take 2 graph papers. Take one graph paper or take a 2 transparency Xerox of it and put one across the other. You'll see the shifting patterns. Okay. This is the space analog of what is called as wave nature of light. There is the space analog of what is called interference, which I tried to capture using this high rise, okay, unsuccessfully. I'll tell you, if you ever get a picture, please send it to me. You take this high rise in between them, and you see the sunrise in between them. As the sun rises, you can see diffraction patterns. Okay, I have not been successful here, but this is what I'm trying to capture, and I have not succeeded. Okay. So if you want to show somebody interference phenomena, this is the way to show it in Bombay. कि ये interference ऐसा होता है. Okay. Or even, sometimes the standard one is, of course, if you just after the first rains, since there is oil on the road, okay, you can see these rainbow patterns. That's another diffraction pattern. Okay. Okay, anyway, so that's either something else I wanted to show you. Yes, yes, ma'am.
You use those patterns you said to detect
Imperfections, yes. I will show it to you. Thank you for asking this question. Okay. I'll give this to you so you can see it for yourself. Please return it at the end. I will come to what you're saying, ma'am. At first I wanted to convince people that this is indeed true. Okay, yes, maybe I'll give it to a small child. Okay, and this also, please. In the back, please. Okay, all right. You can get all kinds of beautiful patterns. In fact, I challenge students who come for the Olympiad program to derive these patterns. And some of them, even the best students in India, those who top in the IIT, they are not able to derive this, to show how these patterns come about. Okay. There's another way you can see this, and if you travel in a second class compartment, local train again, or if you are at a traffic signal, you'll have these street urchins, and she's trying to peddle this for you to you. These are moving patterns of animals. Okay, I always buy them. You can bargain for it, I mean, they'll start with 40 rupees, you can get it for 20. Okay, earlier I could get it for 10. Okay, these were before the movies came in the 30s, the talkies, there was the silent era. And before the silent era, okay, there was these things. For fairy tales were told, Red Riding Hood riding along and the wolf is eating her up or eating her grandmother up or something like that. Here it is. Yes? Yes, whole storybooks were made. Whole storybooks were made like this. Yes. Okay, if anybody else, there's one more I have here, but imperfections, basically they can be used to find out if there is counterfeit currency, for example. Okay. This is an enlarged version of the 2000 rupee note. Put one on top of the other, strain your eyes a little bit, you can see a moire pattern. A distinct pattern is what you look for, and if you find that it is not there, you know that it is a forgery. It's a counterfeit surgery. I'm not sure if India is doing this, but certain countries are using moire patterns to detect if there is a counterfeit surgery, counterfeit notes, currency, not surgery, but currency. Okay.
So, actually, I did not understand this, what to look in that.
See, for example, you have 2 identical patterns. You go Xerox, take a graph paper, make a photocopy of it. Make 2 photocopies on transparency paper. Put one right on top of each other, you'll just see straight through. Correct? But you just twist it a little bit, like if one has got an imperfection, then you'll see these well-defined patterns like what I've shown you here. This is. You have these dark and light bands coming out. Okay, a typical dark and light band is what gives you the idea that there is an imperfection. Like in the C, what you see over here in the C link it's a pattern like this. Okay?
So if the pattern is not there, means there is some counterfeit. Means there has to be
No, see, the pattern has to be there. Okay? If it's one on top of the other, you won't see any pattern. But if you move it, you have to see a distinctive pattern. There may be a pattern, but you're looking for a distinctive pattern which you know is a signature of a proper currency or a counterfeit currency.
Okay, so when there is a little bit deviation between two identical things,
Yes, there is a distinct pattern. You won't see that pattern. Yes, sir. Yes. Who is that? Yes, yeah.
what if the note is what if the note is counterfeit but is the exact same?
If it is, then it is. But you are assuming that if you're making a counterfeit note, you'll make some mistake. Okay. It won't be a perfect copy of the kind of thing that you have in Nasik or something in the printing press. Yes. Okay. But you know, these kinds of things you can see even this kind of, jisko Hindi mein kehte nakashi ka kaam, Urdu mein se, you know, there are these very beautiful patterns you have in architecture. You know, in Lucknow you can see one behind the other. Move your eyes, you can see that moire pattern. Okay. I should use this. Okay. Whoever has taken this may kindly return it at the end of the talk, that's all, because I don't have too many of these. Okay. Now, another thing about Mumbai, the story is not complete if I don't tell you about these great institutions of Mumbai. Okay. The first, we look at the oldest, the Colaba Observatory. It's a magnetic observatory which started in 1826. What does it do? The Earth has a magnetic field. It is about 0.3 Gauss, whatever that means, you know, some 0.3. Okay. It measures the variation, diurnal, seasonal, of the Earth's magnetic field as, you know, basically to a certain very high degree of accuracy, greater than 1 micro Tesla, 1 micro Gauss, greater than 1 micro Gauss. Okay. And it has been keeping this record for about at least 200 years now. Okay. Wait. So I have to tell you a few things about this thing. It is now shifted, of course, to Panvel, but the Colaba Observatory is world famous because it is the only one in the world which has a continuous record for more than 160 years. Even the one in Greenwich and in Paris don't have it, because their record was actually interrupted during the First and Second World War. Ours was not. Okay. The other thing is, ours is the only one in the equatorial latitudes, in the tropics. The others is all in the higher latitudes. Okay. During the great magnetic storm that took place in 1857, the same year that we had our War of Independence, okay, during that great magnetic storm, this is a prized, it's called the Carrington storm. It's named after a British person called Carrington. Okay. This is the one which is the prized record that we have. We have that record at the tropical latitude of the Carrington storm. Yes, sir. What is the purpose? I mean, why do you do it? Okay. One is that it's just observation. Okay. Yeah, the Earth's magnetic field and how it varies and why it varies. Earthquakes cannot be detected that easily, or predicted at least, can be detected. Once that happens, there will be variation in the magnetic record, of course, but it cannot be predicted on the basis of this. Basically, if you go across, say, if you are in Mumbai, and you go across the same latitude, you expect the same kind of magnetic field. If it is larger, you know that there is iron ore. You know that there is some mineral or the other. You know that there is some disturbance or the other. Okay, so that's one purpose. I may also add a couple of things. The Earth's magnetic field has reversed itself. A few million years, it keeps reversing itself. Okay, and it's going to reverse in a, they say, not very far future now. Okay. So this will be the one which will give an early warning signal that the Earth's magnetic field is reversing. Correct?
Then what will happen?
You can't do anything about it. But I mean, you have to grin and bear it, like the Mumbai floods and the Bombay rains. No, but you can actually worry about it and say that, okay, my compasses have to be recalibrated. Many things have to be recalibrated because of that. For example, I have this mobile which has got a magnetic compass inside it. All that has to be recalibrated. Yes, sir. Yes. 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 Why not? Yes, if there is a solar flare, yes, then you can detect all this. Yes, go ahead. Yeah.
So does it differentiate?
Yes, it will. There is a baseline test, and now there is a solar storm. Things come. There is a big magnetic storm coming because of the Earth. The sun is behaving in an odd way. Then you will feel it. Yeah, you will record that. There will be variations and fluctuations in your recording. Okay. Many of these things, by the way, people say. I mean, anybody else wants to say something? Yes, sir.
Just answer to that. This draws out something which is called as a variation chart, magnetic variation chart, which is predicted for next 20 to 30 years, which mariners and aircraft use it to correct their compass for the variation at different locations. It's an internationally global chart which is available for use for navigation. So that is one practical possibility.
Yeah. So that is one, I think the one answer that scientists give is very common, When Faraday was asked, what is the use of your electromagnetic induction? And this is a lady who asked him. So he shot back and said, what is the use of a newborn baby? Or something. So, and then a politician asked, I'm not downplaying your question, but I just thought I'll share this. We are doing it all in a light-hearted moment, so please excuse me. A politician asked, he said, what is the use of electromagnetic induction? Okay, now of course it's used everywhere, of course. Start right from airports where they see if you have got a metal detector or a pistol or something you're carrying. Okay. So he said that, I don't know what it's used for, he said. He was very, very blunt and very honest about it. But he said, one day you're going to tax it. Huh. Yeah, see, go ahead. I will tell you now. This is the story now. There is a good yeah, yes, ma'am.
What will happen if this magnetic reverses and when?
If it reverses, maybe you can answer what would happen. I mean, a lot of things could happen.
This chart will have a redraw for the navigation. And of course, now, as far as practically concerned, we have GPS navigation. So nowadays, we don't depend much upon the magnetic. But absolutely, when GPS fails, we got to go back to the basics.
There is a lot of implications if the Earth reverses its field. Okay, not everything is something which I can chart right now, but maybe I'll look it up and let you know. Okay. Now here is a story about it which I wanted to share with you. It has got to do with trams. There was a romantic era of Bombay called the era of trams. Okay. Here is a tram. Okay. There are all kinds of trams, double-decker tram, okay, single-decker tram, trams with 2 coaches, etc. Trams were actually important means of communication because they went to the heart of the city. They went right into Kolaba, okay, or they went anywhere. They could have gone right into Lokhandwala or something like that. So somewhere else, So they could go in. They were slow, so they were good for business, unlike cars, because cars have promoted malls. The trams promote small business. Okay, they have no end point pollution. That is to say, in generating there may be electricity, there is pollution. But in the end, there is no pollution. And then there is level boarding. The boarding is very good for old people like us and for children. Okay. So they shut down the trams, of course. Here is the story. The trams were shut down in 1964. The trams in Sydney were shut down in 1961. The trams in Melbourne, Australia, by the way, is very interesting, continues. And now they are all going to run on solar energy. So there is not even beginning point pollution that much. Forget about end point pollution. Okay. But the trams which started in 1874, 20 years after the local train started. Okay. In 1900, they decided to electrify it, but it got delayed till 1907. That was because there were objections. Who raised the objection? A gentleman by the name of Nanabhai Moose, who was the director of the Colaba Observatory, put his foot down and he told the British, he was a Parsi gentleman, that you cannot bring the trams into Colaba. If you brought the trams in, there would be a magnetic field due to the current that the electricity is carrying that is very small, that is 0.0004 Gauss, okay, whereas the Earth's magnetic field is 0.31 Gauss, but still that is bad enough that there will be my fluctuations cannot be recorded properly. So he stopped the tram from getting electrified. And he said, give me some time. He went to a similar place in Alibag. In Alibag, they carried out for 2 years the same recording that they did in Colaba. They did what is called baseline testing. After they had baseline tested it, they got the observatory in Colaba in Alibag built. Brick by brick, each brick was tested for magnetism to see that it is not magnetic. And then that observatory was built, and then it was allowed. Okay. Now that is something, it's a story. Many of our directors, I mean, would we wish they were like that. They would also put their foot down in many matters. This is Colaba, this is Alibag. Okay. This is where the observatory is now, and it is worth a deco. You can go and see it. This is the magnetic observatory in Colaba, in Alibag. Okay. Okay. That is as far as this is. There are several great institutions, and I am running out of time, so I will run through a couple of them. This is the Bombay Natural History Society, my favorite, 1883. Okay. It has been, it's a voluntary organization. You have to pay and you have to become a member. Nobody gives you anything. I mean, you just have to contribute to it. In 1912, imagine, long ago, they asked their volunteers or their life members or their members to carry out collection of mammalian species. Over 10 years, they collected 50,000 mammalian species, not one, not two, 50,000, out of which they identified 100 mammalian species as new. An enormous job, given that it's all voluntary. Okay. Yeah, we all do state-supported work, but this is voluntary. These are the other institutions. 1887, the VJTI, the Hafkin Institute, founded by the Ukrainian Mr. Hafkin, who also discovered the vaccine for bubonic plague and cholera. Okay. And I think if it's a rainy day, you can go there. They have a museum. They have a serpentarium for serpents, where you can see. The Tata Memorial Center, a wonderful place, okay, doing great service, 1941. You can be proud of Bombay because of these institutions. The formerly what was known as the Royal Institute of Science, the Tata Institute, where Chai and Wai Outreach Committee is located, the Bhabha Atomic Research Center, of course the IIT. And here there is one which you have not heard of, the Gemological Institute of India, founded in 1971. Okay. The Gemological Society of India, these are all the gems, you can sort of Muktika, Mankiya, Vaidurya, cat's eye, that's called cat's eye. Okay. You would think that what kind of science do they do? You go to Sukhsagar, how many of you know near Chowpatty, they are there on the 3rd floor. They have a wonderful collection of equipment to analyze diamond. They have FTIR, Fourier transform infrared spectroscopy. They have IR visible spectroscopy. They have X-rays. They have photoluminescence spectroscopy. They have all the instruments right there for diamonds and for other gemstones like this. Okay. So they do a good amount of research, all privately supported. No government funding here. Okay. And I was fortunate enough to go there, and I happened to know one of them. And that was the only time, and I took a couple of people along with me, that we got to hold so many diamonds in our hands. I think never again will that happen to me. Okay. So that's all that you can see. You can see this, and that's it. Okay. So, and of course, there is the Indian Women's Scientists Association, 1973. There's a Women's Science Association. Okay. So that's about some of the institutions. I have not exhausted it. I mean, there's a whole lot more. Okay. where you can go on a rainy day, you can go to any one of these and spend some time. Okay. Okay, so that brings me to the end of my talk. There are many things I wanted to share with you, but of course, obviously, I mean, you have been very, very patient, and I've been thankful to you for being patient. But there's one thing that I have to do. Yes?
Sagar will help curate this.
Yes. By the way, I've written a booklet which is a little amateurish, and it contains only a few of these things, called Physics and the City of Mumbai. Okay. You can have it. It is for free. I'm not selling it. Okay. And the only requirement is that you write your email ID and perhaps what you do. That's all. Okay. I know you don't have to, but the email ID, you don't have to put your number down or something. And in fact, I would insist that you don't put your telephone number down. Okay. That is because this is becoming a nuisance. So you can have it. I have about 50 of these or 60. And could you help me distribute it? Not now. It's not yet done. There's one thing which I didn't touch upon, and that's Bombay and Bollywood. And I will end with that. Okay. So Bombay, of course, is the city of Bollywood. And these are all the kinds of things you see in Indian movies, or Hindi movies, if I can say it. Here's this person. He's jumping off in the opposite direction. Not recommended. Okay, right. None of these things happen. And here's this guy crossing the tracks. And the train is right on him. Okay. They do all kinds of things. I'm not interested in analyzing this. See, our inclination is towards physics or romance. So we analyze something like this. Okay. This is the shimmering moonlight. He's a very famous actor of yesteryears, and she is a very famous actress. And they had a lot of chemistry off stage, off screen also, I'm told. Okay. And this is the moonlight. You know how the song ends? Can anybody tell me which movie this is? This is from Avara. Okay. And you know how this movie ends? Okay. Maybe I should show it to you. It only takes 5 seconds, and I will show it to you. Can you hear it? Okay. I will fast forward it and play the end part, which I want you to see. That is how it ends. Okay. Oh, that is the March for Science. Oh, where did my talk go? Which is this one? Can you get it for me? I can't get my talk now. Ah, yeah, that's the talk. Thank you. I go to the. Yeah, okay. So this is how the movie ended. Okay, how the song ended, not the movie. Okay, and when the song ended, there were waves on this lake. I think probably artificially created, but you don't see the ending actually. You don't see them kissing or something or embracing. But they go in a riotous embrace that happens. With this kind of scene. It's very well done. So as usual, I mean, as a physicist, I made a problem out of it. And I gave it as a very difficult entrance test called the Kishore Vaigyanik Protsahan Yojana last year. Okay, so this is how I gave the test. This is the problem I make. Okay, what I did was, and I don't want you to go through this calculation. It's a horrendous calculation. It is basically You have to be a killjoy to do this kind of thing. But any student who is interested, or if you know some student in 10th or 11th, I can run him through the calculation. This is basically the average angle made by the wave with the horizontal, that is alpha. This is the angle made by the moonlight with the horizontal, that is theta. Okay? The shadow length AB, after a long list calculations that you have to do, the shadow length turns out to be 4 times the height of observation into this alpha, this angle, and divided by whatever it's called. I'm really sorry that if you're not in science, you won't trigonometry. It is sine squared theta. Okay. So if your moon is at 30 degrees angle, and you are at a height of 2 meters, your shadow length, and of course this angle which a light breeze makes, the wave makes with the horizontal for a light breeze is about 5 degrees to 10 degrees. That is the angle made by the wave with the horizontal. The angle made by the moon is about 30 degrees. You do this calculation, it's about 3 to 4 meters. You get this long thing, okay. Which means, this has a certain implication that if you give me a picture, I can tell you the height from which the picture was taken. Okay. That is, you can get this height if I know the length AB from that picture. It also means that if theta is small, sine theta is even smaller and the length is longer. Okay. So if the moon is almost on the horizon, just above the horizon, you have a very long sort of reflection of that moon in the lake. Okay. Okay, let's see. Here it is. Same two people. Okay, but another movie. Can anybody tell me which movie? It's a wonderful song, but I will not play it for you. Okay. It's one of the best songs I've heard. If you have the 10 best romantic songs in Hindi movies, this would be one of them. Okay. You see this? This shadow length is small. This reflection, sorry, not shadow. And see this. This is very long. Okay. And I can back calculate and tell you the height from which it was taken. Okay. There's another one. So we don't want the stunt part of it. The physics of the stunt is there in many places, but the romance of it. This is from another famous movie where this person who is dancing, Anarkali, her image is reflected in the 1,000 mirrors upstairs. It's on the roof. There are thousands of mirrors in the roof, and you can see all of them done long, long ago. Now, how it was done is not very clear to me. But I do know that this glass that made it, it's called Belgian glass, it was not imported from Belgium. Okay, it's called Belgian glass. It was actually made in Firozabad in Western UP and gotten over here. And I set up in Mehboob Studio in Bandra. Okay. There is a story, I don't know if it is true, that after it was recorded, Mehboob Khan, whoever it was, K.Asif or Mehboob Khan, I forget, he destroyed that whole set. He didn't want anybody to replicate it. This is another one from more recent times, from Bajirao Mastani. Okay. Here is Bajirao standing here. And here is Kashibai, who upstairs, who sees his image in a curtain, in a diaphanous curtain. Okay. What happens is that there is a mirror over here, there is a mirror in Kashibai's room, okay, and then these two reflections give you this reflection of Bajira. How does that happen? It's not very difficult. This is the easy one actually. Okay. Okay. If there is an object, that object is sent to a concave mirror, which is then reflected into a plane mirror, and which is then put on the screen. As simple as that. In fact, I have, if somebody is interested, I have brought these kinds of mirrors, one concave and one plane mirror, and we can just see how it is done. Okay. Okay, so finally, this last slide. We all go to the sea, we all eat pani puri. How much water is there in that pani puri? This is the last one. How much? Any other guesses? Yeah. It's about 15. On an average, pani puri has 15 cc. So, it's actually I recommend it for kids who have diarrhea. Oral rehydration therapy, the Mumbai way, is to have 6 pani puris, but the water should be clean and should be all dal jeera pani, which is very good. Okay, so it is all recommended. Okay, right. And that's it. Thank you very much.